Hello, my name is Stefan, and today I'll be talking about the algorithms and the functions that we use to create our 8 puzzle game and our solver. So to start off with, we import heap push and heap pop for our future needs. And the goal we want is to have blank on the top left, then the numbers followed from 1 to 8 in a numerical order. And as you can see here, this function show board allows us to categorize number from the top three, bottom three, and the middle three. So first, so in our goal state it would be blank 1, 2. Then our second would be 3, 4, 5, and our third row would be 6, 7, 8. And then we have this function which says check solvability, which we didn't actually know we had to add later. That some configuration of a 3 by 3 grid of 8 puzzle are not actually solvable. So we had to add this. So inversion basically means that whenever there's a certain number of tiles in a puzzle, there are certain pairs, and whenever the first number in a pair is bigger than the second number, that counts as an inversion. And if we have an odd amount of inversions in a program, that means it's not solvable. Or in this case, in 8 puzzle, it will be solvable. So you would always would look for even number of inversions, as seen here. Return inversion divided by 2 should equal 0. If it is, then it's solvable. Then we have our heuristics that we use, which is a distance estimate function. Here we use the Manhattan distance heuristics, which basically allows us to, well, first to map our map our tiles our indexes in a coordinate fashion. So each tile has their own specific coordinates which align with rows and columns. So rows are x values and columns are y values. So for instance, 1 1 in the goal state would be in row 0 and column 1. So the columns basically go 0 0 0 1 0 2. Then the next one would be 1 0 1 1 1 2, and the last one would be 2 0 2 1 2 2. So those are the coordinates. And what this basically does is it takes the current row value of the tile, subtracts from the goal row, does the same for the current column and current goal column, and then it takes the whatever the values are, adds it together, and you get the absolute value of that. So there's no negative numbers, and whatever that value is, that is the value of Hn, the heuristics value of Hn, which is later put into the A star algorithm function of Fn equals G of Gn plus Hn, and G of n is the number of moves per state. So that's calculated later, and you add that to the this heuristic value, which is h of n, then you get f of n, which is the total number of moves that you need to do to get to the goal state. And from there on, we have the possible moves, which indicates the possible ways that from the blank space we can move. And for that, we have to create some boundaries and allow and legal moves so the algorithm doesn't just go off the board. So for instance, if you're on the top corner, which is 0 0, the only two places you can swap toward is down or right. You can't go left because you're touching the wall. You can't go up because you're also touching the boundary. So the boundaries allows us to keep within the grid. Then this is how this is the solve function, which basically says if the start board equal to the goal, then well you got lucky and it's already solved. And then we check if it's solved or not back to the inversions, and it checks for that. If it's not, then it returns none. There's you can't, and then you have to. If it doesn't, then it follows through and it goes here where it's priority queue. So which basically means back to the A star algorithm, whatever the lowest value of f of n is, it takes that and it keeps expanding on that until it slowly goes to the goal state where the f of n value would be 0. It keeps popping the lowest value and continues expanding until it gets to the goal state. And after doing so, we have a trial case that we have here to just test out this code. But we're not gonna do it because we will actually show the full version. And this is our this we use Tinker to create our front of the app, the little mini version of the app. It has two buttons. One is to randomize and one is to solve. It also visualizes the keys moving. We have let me see. We have a timer here, so that's how fast it moves, so you can visualize it properly instead of just doing it in the back end, just giving you the clean goal state. That way you won't really able to see how they move. And it also calculates the number of moves you did. That wasn't really needed, but we did it because one of the questions in the project was, what do you want to achieve with this AI agent? And and one of our goal was to uh, create a memory-based agent which can take memory, which can uh, remember the attempts it did previously, gain knowledge from that, and move forward with that and do faster and faster. So the counter of moves is just a way for us to see if we're able to make our AI agent faster if needed. So now we're just gonna run the program and see how that works. Let's run it. It's running. All right. So this is our initial goal state. That's the one I put in the our report that we'll be using. So let's solve this one. We click solve, and it shows them moving by slowly. Let's give it a second. It will be solved. Should take around 25 to 30 moves. Yeah, we solved in 26 moves. Okay, let's do it again. Now we randomize it. Another move, another board state, initial board state. Click solve. It will solve now. So yeah, it solved in 16 moves. That board initial board state might have been more closer, and we can might have created a data sheet of how the different board states affect different amount of moves. And that's one study we could do on our project later on, maybe if you want. But that's it for our project. Thank you for watching. Have a good night. Bye bye.